Hello, I'm Brain Rainey, and welcome to the Motion of a Falling Object Lab. Students will record the motion of an object falling straight down and analyze its motion using Tracker. This object should start from rest and fall slower than a rock. Since the object must fall slower than a rock, there must be some force acting on this object, as mass is insignificant to how fast an object falls. This is proven over 400 years ago by Galileo. It can also be shown through derivation of this velocity update formula through the momentum principle, as seen here. And this can be simplified to that the final velocity is equal to g delta t. Note that there is no mass included there. When the only force is gravity, an object starts from rest. Since it's going to be a different velocity, or slower, we know that there must be a different force, an extra force. And then students will then compare their experimental position versus time results with two separate prediction models, one that includes a drag force and one that does not. And here are my results. The blue is the experimental, the yellow is the model with the drag, and the red is the model without the drag. And you can see the model with the drag and my experimental positions were very similar. This is one because I tried to make it that way, but two, I mean, they stay on a very similar path this whole time. It's not just the endpoints, which I was able to fix, that are very similar. And there's this huge gap in between the experimental position, final position, and what the predicted final position would be if there was only the force of gravity. And it's actually over 2 times as much. And this is shown, or this is proven to be false because there is a drag force, and that's why there's such a large discrepancy, because this drag force must be very large. And as you can see, here's my video. I used a washcloth, I dropped it, and it did not go exactly straight, but still led to pretty similar results. And after performing the experiment, I tracked the center of mass of the towel 36 times in Tracker, as you saw back there. And the graph is somewhat between linear and exponential. You can see parts here are very linear, but towards the beginning it seems more exponential. And the reason why is towards the beginning it might be more exponential because the only force is gravity, and there might be a very small drag force, but it's only gravity for the most part. And as we'll see later, when it's just gravity, constant force, it will lead to a negative slope. Now, once the velocity builds up, the drag force increases, almost canceling out with that the forces, which leads to a constant slope of a straight line. And in this case, it's negative since it was falling. All right. This was the graph I was talking about earlier that I created in GlowScript of when only force was gravity, and here's one where the drag force is included, as you can see by this arrow. And then I also created an Excel sheet to calculate the positions and the velocities of the models without and with drag. And I have included the B constant, which is used for the drag force. Terminal velocity. Now, over to the left is a section of my Excel data, which is used to make the position versus time graph towards the beginning of the presentation, the one with all three. And the velocity for the model with a drag, starts to reach negative 2.6. As you can see here, it's very similar throughout. It picks up, but then it starts to slow down and starts to reach a terminal velocity, you can call it. But the other graph that has no drag just continues to build and build and build all the way up to negative 11 meters per second. And that's because there is no countering force, and it will continue to build indefinitely at a constant rate. And this may beg a question: if an object is thrown down, or the initial velocity is different, will that affect its terminal velocity? And as you can see by this model, it does not. At the beginning, its velocity is much larger, but it will close in this gap, and this is due to the fact that the drag force is equivalent to it's proportional to the velocity squared. And once it reaches a certain velocity squared, it will be able to counteract that gravity force, which is never changing. Yep. Here's my code. I changed the initial conditions, including the mass, the initial position, the delta t, the g, and the b constant, which I showed earlier in my Excel spreadsheet. And then I used all these constants to create a gravity force and a drag force, as seen here, both in the y components. And then I add them together and plug that into the velocity update formula as shown at the very beginning of the presentation. And I use that velocity in the position update formula. And I also change these so you can see those arrows. And yeah, that's basically it for my presentation. And thank you for watching.